The echidna moves slowly across the Australian interior, a low mound of spines and fur advancing over red dirt that has been baked hard by the sun. Its posture is almost comical at first glance, head down, body rocking, nose sweeping the ground with obsessive focus. From a distance, it barely registers as an animal at all. It looks like debris given motion, a misplaced bundle of sticks crawling through spinifex and ironstone. But this illusion is its first advantage. In a landscape where survival often depends on conserving energy and avoiding attention, the echidna does not advertise itself. It works quietly, methodically, as if the continent itself were pulling it forward grain by grain. This is not just another small mammal foraging in the outback. The echidna belongs to a lineage so old and strange that it challenges the neat categories humans use to understand animals. It is a monotreme, one of only 2 kinds of mammals on Earth that lay eggs instead of giving birth to live young. The other is the platypus, an animal equally infamous for defying expectations. Together, they represent a surviving fragment of an ancient mammalian experiment, one that branched off before evolution settled on the familiar blueprint of placentas, nipples, and rapid reproduction. The echidna is not a halfway point between reptiles and mammals. It is something else entirely, a parallel solution that never went extinct. Reproduction is where this strangeness becomes impossible to ignore. During breeding season, the female echidna develops a temporary pouch on her belly, an evolutionary improvisation rather than a permanent structure like that of a kangaroo. Into this pouch, she deposits a single, soft-shelled egg, leathery rather than brittle, more reptile than bird. 10 days later, the egg hatches, releasing a creature so underdeveloped it barely qualifies as an animal by human standards. The newborn, known as a puggle, is blind, naked, and gelatinous, little more than a wrinkled embryo with a mouth. There are no nipples waiting for it. Instead, milk oozes from specialized patches of skin, and the puggle laps it up directly, pressing its face into the mother's belly. This is mammalian nourishment delivered in a way that feels almost pre-mammalian, as if evolution stopped halfway through the instruction manual and decided it was good enough. While the young develops in the safety of the pouch, the adult echidna returns to its primary occupation, eating ants and termites by the tens of thousands. This is where its body reveals its true purpose. The echidna's skull is elongated into a narrow, tubular snout, rigid and unyielding, built not for biting or tearing, but for probing. There are no functional teeth. Chewing would be useless here. Instead, deep inside that snout lies one of the most specialized feeding tools in the mammal world. A tongue that can extend nearly the length of the animal's head, coated in sticky saliva, snapping in and out with astonishing speed. Each flick is a harvest, pulling insects from tunnels and chambers hidden beneath soil, bark, and rotting wood. Over the course of a single night, an echidna can consume thousands of prey items, dismantling entire insect colonies without ever tearing open the mound that shelters them. This feeding strategy only works because the echidna can find prey without seeing it. Its eyesight is mediocre, its hearing unremarkable, but its snout is packed with electroreceptors, specialized sensory cells that detect tiny electrical signals produced by the muscle contractions of living insects. Ants marching underground, termites shifting within sealed galleries, larvae writhing in damp soil all betray themselves through microscopic electrical activity. To the echidna, the ground is alive with invisible movement, a shifting map of edible signals. As it sweeps its snout side to side, it is not sniffing so much as scanning, reading the land like a living circuit board. This sense is so sensitive that even the heartbeat of buried prey can be detected under the right conditions, turning the echidna into a biological metal detector tuned not for awe, but for life. In ecological terms, this makes the echidna a quiet regulator. Ants and termites are ecosystem engineers, capable of reshaping soil structure, nutrient flow, and vegetation patterns. Left unchecked, they can overwhelm certain habitats, stripping seedlings and destabilizing plant communities. The echidna does not eradicate them, it cannot, but it trims populations continuously, exerting pressure that keeps colonies mobile and adaptive. Its slow, steady feeding is the opposite of a dramatic predator strike. Yet over years and decades, it shapes insect behavior and distribution just as effectively. This is dominance without spectacle, influence exerted through patience rather than power. When threatened, the echidna reveals another layer of evolutionary stubbornness. It does not flee quickly, it cannot. Instead, it deploys defenses that rely on geometry and persistence. Powerful forelimbs equipped with long claws dig rapidly into the soil, and the animal sinks downward, levering earth over its back until only a dome of sharp spines remains exposed. Each spine is rigid, keratinized, and anchored in muscle, capable of swiveling slightly to resist pressure. Predators attempting to bite or paw at this living pincushion quickly learn that there is no safe angle of attack. Dingoes, foxes, and large birds of prey have all tested the echidna and failed. Even vehicles pose a lesser threat than expected. When rolled into a ball, the echidna can sometimes wedge itself against the road surface, resisting being flipped or crushed. These defenses are not just physical, but behavioral. The echidna is patient to a fault. It can remain motionless for hours, conserving energy while danger passes. Its metabolic rate is unusually low for a mammal, allowing it to function efficiently in cold alpine regions as well as scorching deserts. Unlike most mammals, it does not maintain a tightly regulated body temperature. Instead, it allows its internal temperature to fluctuate with environmental conditions, reducing the energetic cost of thermoregulation. This reptile-like flexibility is not a weakness. It is a strategic retreat from the constant metabolic demands that drive many mammals to exhaustion. This combination of traits, egg-laying reproduction, milk without nipples, electroreception, variable body temperature, toothless feeding, and extreme defensive specialization, should not work together. By conventional evolutionary logic, the echidna looks like a compromise animal, burdened with outdated features. Yet it persists across nearly every habitat in Australia, from tropical forests to snow-covered mountains. It has survived climate shifts, megafaunal extinctions, and the arrival of invasive predators. Its apparent awkwardness is deceptive. Every odd trait is integrated into a coherent survival system honed over millions of years. What the echidna ultimately represents is not evolutionary confusion, but evolutionary refusal. It is a mammal that did not follow the dominant script, that retained ancient solutions because they remained effective. In a continent defined by scarcity, unpredictability, and harsh extremes, the echidna thrives by ignoring speed, aggression, and excess. It invests in sensing rather than seeing, in persistence rather than pursuit, in defense rather than escape. While other animals race to adapt, the echidna simply endures, vacuuming life from the soil with quiet efficiency. Seen this way, the echidna is not a relic. It is proof that evolution does not move toward complexity for its own sake. Sometimes it preserves a strange, stubborn design because that design works. In the red dirt, under the blistering sun, the spiky vacuum keeps moving, nose down, reading the electrical whispers of a world beneath the surface, laying eggs like a reptile, feeding young like a mammal, and surviving in a way that still defies expectation. In the open woodlands of northern Australia, the heat sits low and heavy, pressing down on bark, dust and leaves, bleached pale by months without rain. Tree trunks are cracked and peeling, their surfaces a mosaic of greys and browns that seem deliberately designed to erase anything standing still. On one of these trunks clings a lizard, so perfectly matched to the background that it barely registers as a living thing. Its body is flattened, limbs splayed, head angled downward, eyes half-lidded. It does not flee when birds pass overhead. It does not flinch at the movement of insects nearby. In this moment, survival depends on anonymity. To be seen is to be eaten. Then the illusion detonates. With a sudden snap of motion, the animal erupts outward. Its mouth flies open, its jaws stretching wide in a silent scream, and from behind its head, a vast circular frill explodes into place, bright orange, yellow and red, ringed with dark margins like a warning sign written in flesh. What was once a slim, forgettable reptile becomes a living disc, nearly twice its original apparent size, vibrating with tension and color. The air seems to recoil from it. Predators hesitate. The woodland pauses. In a fraction of a second, the frilled lizard has rewritten the rules of the encounter. This transformation is not accidental, nor is it mere theatrics. The frill is a precisely engineered structure, folded tightly against the neck when not in use, its skin pleated like a collapsed umbrella. Thin rods of cartilage radiate outward from the skull, anchored near the jaw hinges, held in readiness by connective tissue and muscle. When the lizard opens its mouth forcefully, those rods are pulled forward and outward, snapping the frill open in a rapid, coordinated movement. There is no delay, no gradual unfurling. The display is instantaneous, designed to overwhelm the sensory systems of anything watching. Color floods the scene, shape expands violently, and the sudden contrast between stillness and explosion triggers hesitation in predators that rely on rapid decision-making. The frill is not just large, it is loud in every biological sense. The open mouth exposes pale tissues and dark throat lining, while the lizard hisses sharply, forcing air through its lungs in a controlled exhalation that adds sound to the visual assault. Together, these signals create a moment of confusion. Is this prey or something else? Is it dangerous? Is it venomous? In ecosystems where mistakes are costly, hesitation alone can save a life. Most predators, snakes, birds of prey, even medium-sized mammals, abort the attack at this stage. The lizard does not need to fight, it only needs to convince. What makes this strategy remarkable is how completely it contradicts the usual rules for animals of this size. Small reptiles typically survive by minimizing detection, camouflage, stillness, and rapid escape. Noise and color are liabilities. The frilled lizard inverts this logic. It hides only until discovery, and once seen, it becomes impossible to ignore. This is not a passive defense, but an escalation, a calculated gamble that the shock of transformation will outweigh the risk of exposure. In evolutionary terms, it is a high-stakes bluff, one that works often enough to be reinforced across generations. Yet the frill is not merely a shield against predators, it also plays a role in communication within the species. Males use it during territorial disputes, facing rivals head-on with frills fully deployed, bodies elevated, and mouths agape. These confrontations are loud, dramatic, and usually resolved without physical contact. Size, color saturation, and posture convey information about health, strength, and motivation. The frill becomes a billboard advertising genetic quality, turning fear into a social signal. In this way, a structure that likely began as a modest skin fold for display or thermoregulation was gradually exaggerated by sexual selection, pushed further and further toward excess, because those who displayed most effectively survived and reproduced. Thermoregulation still lingers beneath the spectacle. The frill is rich in blood vessels, and when extended, it can act as a heat exchange surface, absorbing warmth in the cool mornings and shedding excess heat when temperatures climb. In the dry woodlands, where shade is scarce and thermal extremes are routine, this dual-use design offers subtle but meaningful advantages. The same structure that startles predators and rivals can also fine-tune the animal's internal temperature, linking behavior, physiology, and environment into a single adaptive system. When the display fails, when a predator refuses to be fooled or a threat advances too quickly, the frilled lizard reveals its final trick. It drops from its vertical perch to the ground and breaks into a sprint, rearing up onto its hind legs with surprising ease. The tail lifts and stiffens, acting as a counterbalance, while the front limbs tuck close to the body. For a brief burst of speed, the lizard runs bipedally, its posture uncannily reminiscent of small theropod dinosaurs. This is not sustained locomotion. It is a short, explosive dash designed to create distance and reach the nearest tree. The frill collapses against the neck as it runs, streamlining the body and reducing drag, the transformation reversing itself as quickly as it appeared. This bipedal sprint is not a gimmick. It emerges naturally from the lizard's anatomy and behavior. The hind limbs are long and powerful, the pelvis angled to support rapid extension, while the center of mass shifts backward during acceleration. When startled, the front limbs simply become unnecessary. Evolution did not design the frilled lizard to run like a dinosaur, but the result is an echo of deep time, a reminder that the boundary between modern reptiles and their prehistoric ancestors is thinner than it appears. In moments of crisis, the animal taps into an ancient locomotor pattern that prioritizes speed and balance over stability. Understanding how such an extreme combination of traits evolved requires stepping back from the spectacle and tracing smaller changes across generations. The frill likely began as a modest extension of skin around the neck, perhaps used for display or temperature control. Individuals with slightly larger folds may have appeared more intimidating, gaining marginal survival benefits. Over time, selection favored those whose displays triggered hesitation more reliably. Musculature strengthened, cartilage extended, and coloration intensified. Similarly, upright sprinting may have started as a brief loss of balance during acceleration, later refined into a functional escape tactic as those who could run farther or faster reached safety more often. No single leap produced the modern frilled lizard. Instead, a series of incremental exaggerations accumulated into something that now looks outrageous. From an ecological perspective, this strategy allows the frilled lizard to occupy a niche that balances exposure and escape. It forages in open woodland, where insects are abundant but cover is patchy. It relies on trees for refuge, sprinting vertically to escape ground-based predators and dropping to the ground to evade aerial threats. Its diet of insects and small invertebrates links it to seasonal cycles, with activity levels rising during warmer months when prey is plentiful. The frill, sprint, and arboreal habits together form a cohesive survival package tuned to a landscape where hiding spots are limited and visibility is high. The frilled lizard shouldn't exist only if survival is imagined as a narrow path defined by caution and concealment. Instead, it demonstrates that exaggeration can be just as effective as invisibility. By committing fully to intimidation, by becoming louder, larger, and more dramatic than expected, it forces predators into a moment of doubt. That hesitation is enough. In a world where fractions of a second determine outcomes, turning fear into a weapon can be more powerful than any tooth or claw. Seen in this light, the frilled lizard is not a novelty act or a living meme. It is a refined product of evolutionary pressures that reward decisive transformation. Flat and forgettable when calm, explosive and overwhelming when threatened, it embodies a survival philosophy built on contrast. It does not merely run from danger or vanish into the background. It confronts the moment head-on, rewrites the visual rules of the encounter, and then, only if necessary, runs like a ghost of the dinosaur age, vanishing back into the trees as abruptly as it appeared. The water off southern Australia is colder than most people expect. It rolls in from the Southern Ocean, heavy and clear, carrying long forests of kelp that sway in slow motion beneath the surface. Sunlight filters down in pale shafts, fractured by drifting fronds and suspended particles, and everything moves as if time itself has thickened. There are fish here, plenty of them, but they are difficult to separate from the background. Color and shape blur together in this submerged woodland, where survival favors anything that can dissolve into the scenery. At first glance, nothing stands out. The reef looks empty. Then a leaf moves. Not a sudden flick or dart, but a subtle, deliberate shift. One frond of seaweed, adjusting its position against the current. It drifts sideways, pivots slightly, and then advances with a motion so gentle it barely disturbs the water around it. What seemed like plant matter resolves into anatomy. Beneath the illusion is a fish, elongated and rigid, its body traced with filigrees of flesh that mimic kelp blades and torn algae. This is the leafy sea dragon, an animal that does not hide among plants, but becomes one, blurring the boundary between organism and environment so completely that even trained eyes struggle to track it once it stops moving. The sea dragon's body is built on a pipefish framework, long, narrow, encased in bony plates that limit flexibility but provide protection. There is no streamlined muscular form here, no suggestion of speed or power. Instead, leaf-like appendages sprout from the head, neck and body in irregular patterns, each one shaped and colored to match the surrounding weed. These appendages are not fins. They do not contribute to propulsion or steering. They exist solely for deception. Their edges are serrated, their surfaces mottled with greens, yellows and browns that change subtly with age and habitat. Algae often grows directly on them, enhancing the disguise. The result is an animal that appears fragmented, broken into pieces of plant matter rather than assembled as a coherent predator. Movement is where the illusion becomes nearly perfect. True fins are reduced to two tiny translucent structures, one along the back and one near the neck. They beat rapidly, almost invisibly, generating just enough thrust to counteract the current or inch forward. There is no sweeping tail motion, no sudden acceleration. The sea dragon hovers, drifts and pivots, its body aligned with the flow of water so that it never creates a clean silhouette. Predators that hunt by detecting outlines see nothing worth pursuing. Prey that rely on motion cues register only background noise. The animal is not trying to be invisible in the absence of movement. It is invisible because it moves exactly like everything else. This strategy is particularly effective in the kelp forests and seagrass meadows the sea dragon inhabits. These environments are visually dense but structurally complex, filled with vertical and horizontal elements that break up shapes and scatter light. Fast swimmers risk collision and exposure. Ambush predators dominate, relying on surprise rather than pursuit. The leafy sea dragon takes this logic to an extreme. It does not ambush with speed, it ambushes with inevitability. By the time prey recognizes it as a threat, the distance is already closed. Feeding is quiet and precise. The sea dragon preys on tiny crustaceans, mysid shrimp, amphipods, and larval forms drifting among the weeds. Its snout is long and narrow, forming a rigid tube with a small mouth at the end. There are no teeth. Instead, feeding relies on suction. When prey comes within range, the sea dragon opens its mouth rapidly, creating a localized vacuum that pulls the animal inside before it can react. The entire event lasts milliseconds and produces almost no visible disturbance. There is no chase, no strike, only disappearance. In a habitat where energy must be conserved and opportunities are unpredictable, this method is brutally efficient. This feeding style shapes the sea dragon's daily rhythm. Rather than patrolling territory or defending resources, it drifts continuously through productive areas, sampling the environment as it goes. Success depends on patience and positioning rather than aggression. The animal must remain aligned with currents, choosing angles that carry it past dense concentrations of planktonic prey without revealing its outline. In this way, the sea dragon becomes part of the water's architecture, a mobile extension of the kelp forest itself. Reproduction introduces another layer of evolutionary inversion. Like seahorses and other members of the Syngnathidae family, leafy sea dragons reverse the typical roles associated with parental investment. During courtship, the female transfers her eggs to a specialized brood patch under the male's tail. Each egg is embedded in individual cups of vascularized tissue where it is anchored, oxygenated, and protected for weeks. The male regulates blood flow to the patch, controlling oxygen delivery and waste removal while the embryos develop. This is not passive transport. It is active incubation, performed by an animal that already appears fragile and exposed. The brood patch itself is a marvel of integration. Its structure balances the need for protection with the need for gas exchange, allowing embryos to develop in open water without being smothered or swept away. During this period, the male's behavior changes subtly. He becomes more deliberate in his movements, avoiding strong currents and high-risk areas. The added drag of the eggs makes rapid adjustment difficult, reinforcing the sea dragon's reliance on camouflage rather than escape. Survival during this stage depends entirely on remaining unremarkable. Once hatched, the young are immediately independent, miniature versions of the adults with proportionally fewer appendages. They drift into the plankton-rich shallows where mortality is high and only a fraction survive. There is no further parental care. The species relies on numbers, timing, and concealment rather than protection or aggression. This reproductive strategy aligns perfectly with the adult's lifestyle. Minimal interaction, minimal conflict, maximum integration with the environment. From an evolutionary perspective, the leafy sea dragon represents an extreme commitment to a single solution. Most animals hedge their bets, balancing camouflage with speed, armor with weaponry, or stealth with escape. The sea dragon does none of this. It is slow, lightly armed and incapable of rapid flight. Its bony plates provide some protection, but against large predators they are not decisive. Its survival rests almost entirely on not being recognized as an animal at all. This raises a deeper question about what success looks like in nature. The sea dragon does not dominate its environment in the traditional sense. It does not control territory or exert top-down pressure on food webs. Instead, it occupies a narrow ecological niche defined by visual complexity and low energy flow. In that niche, it is extraordinarily effective. By blending so completely into the kelp forest, it avoids predation while exploiting a steady stream of small prey that faster, more conspicuous fish cannot access without drawing attention to themselves. There is also a cost to this specialization. Habitat degradation hits sea dragons hard. Loss of seagrass beds, kelp die-offs from warming waters, and increased turbidity all erode the visual structures the species depends on. Without the right background, the illusion fails. Conservation efforts recognize this vulnerability, protecting not just the animal, but the plant communities it mimics. The sea dragon cannot be separated from its environment without ceasing to function as it evolved to. Calling the leafy sea dragon evolutionarily insane is tempting because it violates intuitive expectations. It looks decorative, excessive, even impractical, yet every flourish serves a purpose. The appendages break up outlines. The slow movement minimizes detection. The rigid body stabilizes orientation in moving water. The male brood patch ensures reproductive success without exposing eggs to open currents. What appears ornamental is, in fact, optimized to an almost obsessive degree. In the kelp forest, speed is not always an advantage. Strength is not always decisive. Sometimes the winning strategy is to become background noise, to look so useless, so plant-like, that nothing bothers to test whether you are alive. The leafy sea dragon embodies this philosophy completely. It does not chase the world. It lets the world drift past, selecting what it needs and discarding the rest, unseen and unchallenged. As the water darkens with depth and the kelp thins, the sea dragon slows and aligns itself with a new patch of weed. The fins beat invisibly, the appendages sway. Once again, the predator becomes a plant, and the reef returns to stillness, carrying on its slow, cold dance with a hunter hidden in plain sight. The billabong looks calm in the early heat, its surface broken only by faint rings where mosquitoes rise and fall. Reeds stand motionless at the margins, cicadas buzz from the tree line, and the air above the water seems crowded yet strangely peaceful. Midges drift in loose clouds, small flies hover, hesitate, land, and lift again. Everything moves slowly enough to track, until it doesn't. A sudden flash cuts across the scene, a metallic streak that appears and vanishes in less than a blink. One insect is gone. There is no splash, no struggle, no warning. Where there was motion a moment ago, there is only empty air. The dragonfly has passed through. It does not announce itself with noise or color at first glance. Its arrival is defined by absence, the disappearance of prey. Only after the strike does the predator become visible, hanging in the air above the water with unsettling stability, wings beating so fast they blur into transparency. Its body is long and rigid, aligned like a projectile, head locked forward. This is not the erratic flight of most insects. It is controlled, deliberate, and final. The dragonfly is not reacting to chaos. It is imposing order on it. The head is where that control begins. Dragonfly eyes dominate the skull, swelling outward until they nearly meet, wrapping the head in a hemispherical sensor array. Each compound eye contains tens of thousands of individual lenses, each sampling a tiny slice of the visual world. Alone, a single facet sees almost nothing. Together, they create a visual field that approaches 360 degrees with only a narrow blind spot directly behind the insect. More important than coverage is specialization. These eyes are tuned for motion. Static backgrounds fade into irrelevance, while even slight deviations, a wing beat, a twitch, a drifting silhouette, are amplified. The dragonfly does not see the world the way humans do. It sees change. In the shimmering air above water, where reflections and glare confuse most animals, dragonfly vision gains another advantage. Their eyes can detect polarized light, allowing them to separate reflections from real objects and distinguish insects from the glittering surface beneath them. This matters in environments where prey often flies low over water, exploiting reflections to confuse predators. For a dragonfly, the trick does not work. The billabong is not a visual maze, it is a data field. That data feeds directly into a flight system, unlike anything else in the insect world. Dragonflies have 4 wings, arranged in 2 pairs, and each wing can be controlled independently. Unlike most insects, which link wing pairs together for efficiency, dragonflies sacrifice simplicity for control. The forewings and hind wings can beat out of phase, change angle independently, and even reverse their stroke mid-flight. This allows the insect to hover, glide, accelerate, decelerate, and move backward without turning its body. Direction changes are instantaneous. There is no banking arc, no gradual curve. The dragonfly simply goes where it decides to go. Aerodynamically, this creates complex interactions between wings. The wake of the forewings enhances lift on the hindwings, increasing efficiency during slow flight, while independent strokes allow rapid bursts of speed when needed. The body itself contributes little to lift. It serves instead as a stabilizing mass, keeping the center of gravity aligned during violent maneuvers. Legs are held forward in a basket-like formation during hunting flights, ready to scoop prey from the air without disrupting flight dynamics. Every part of the body is subordinated to one goal: intercepting moving targets. The result is aerial performance that exceeds what intuition suggests an insect should be capable of. Dragonflies can accelerate rapidly, brake mid-air, and pivot around a fixed point. They can patrol territories for hours, adjusting altitude and position with minimal energy expenditure. When prey appears, there is no chaotic pursuit. There is a calculation. Dragonflies do not chase in the way most predators do. They do not lock onto prey and follow its path, reacting to each evasive move. Instead, they predict. Neural circuits in the dragonfly brain calculate the future position of a moving target based on its speed and direction, then guide the insect toward that point of interception. The dragonfly flies not where the prey is, but where it will be. This strategy minimizes flight time, reduces energy costs, and leaves prey with little opportunity to react. By the time the target detects danger, the dragonfly is already there. What makes this remarkable is not just the behavior, but the hardware running it. The dragonfly brain is tiny, weighing a fraction of a gram, yet it performs computations that mirror guidance systems used in missiles and aircraft. Specialized neurons respond selectively to small moving objects against complex backgrounds, filtering noise and prioritizing relevant signals. Once a target is locked, the system maintains a constant bearing angle, a mathematical approach that ensures collision if both objects maintain speed. This is not learned behavior, it is built in, refined by evolution long before humans named it. This precision makes dragonflies devastatingly successful hunters. Studies have shown capture success rates exceeding 90%, far higher than most vertebrate predators. Mosquitoes, flies, and other small insects do not merely face a predator, they face an aerial system optimized to remove them from the environment. At the scale of the billabong, dragonflies exert significant pressure on insect populations, shaping which species thrive and when. They are regulators, trimming swarms before they can explode, influencing disease dynamics by consuming vectors like mosquitoes long before humans intervene. Their dominance does not begin in the air. Dragonfly life starts underwater, as larvae known as nymphs, and here the story becomes even darker. In the mud and vegetation at the bottom of ponds and streams, dragonfly nymphs are ambush predators armed with a unique weapon, a hinged, extendable lower jaw called a labium. This structure can shoot forward in milliseconds, snatching prey with hooked tips and dragging it back to the mouth. Tadpoles, small fish, and other aquatic insects all fall victim. The same predictive logic that governs aerial hunting applies here as well. Movement is detected, distance is judged, and the strike is executed before prey understands what is happening. This aquatic phase can last months or years, depending on species and conditions. During this time, the nymph grows, molts, and refines the musculature and neural circuits that will later power flight. When the time comes, it climbs out of the water, anchors itself to vegetation, and undergoes one of the most dramatic transformations in the insect world. The adult dragonfly emerges, wings unfolding and hardening, systems switching from aquatic respiration to aerial performance. Within hours, it is airborne, a predator reborn into a different medium. The dragonfly's evolutionary history explains why this design feels so uncompromising. Its lineage stretches back more than 300 million years, to a time when Earth's atmosphere contained higher oxygen levels and insects grew to enormous sizes. Fossil relatives of dragonflies, often grouped as griffinflies, had wingspans approaching 70 centimeters, rivaling modern seabirds. They ruled ancient swamp forests as top aerial predators long before birds or bats existed. When oxygen levels dropped and ecosystems changed, size decreased, but the core design remained. That persistence is telling. Evolution is ruthless with inefficiency. Designs that do not work are discarded, modified, or replaced. The dragonfly's basic blueprint, compound eyes optimized for motion, independent wings, predictive hunting, has endured with relatively little change because it did not need improvement. Minor refinements accumulated, but the system was already near optimal for its role. In evolutionary terms, the dragonfly is not an ancient relic struggling to keep up. It is a solution that arrived early and never became obsolete. This raises the unsettling question of why it shouldn't exist. Insects are often imagined as fragile, reactive, and simple, creatures driven by instinct rather than calculation. The dragonfly breaks that narrative. It is fragile in structure, yes, a lightweight exoskeleton, delicate wings, a body that can be crushed easily by a careless hand. Yet within that fragility runs a control system capable of outperforming many larger animals. It carries a ballistic computer in a head the size of a fingernail and uses it to win almost every pursuit it engages in. Its success also exposes a deeper truth about evolution. Complexity does not require size. Intelligence in the functional sense of processing information and acting on it, can arise wherever selection pressures demand it. For dragonflies, the pressure was clear. In a three-dimensional environment crowded with fast-moving prey, only those capable of predicting the future survived. Over millions of years, that demand sculpted neural circuits and sensory systems until the insect became what it is today, an airborne executioner with no wasted motion. As the sun climbs higher over the billabong, dragonflies continue their patrols. They skim the surface, hover above reeds, dart into open air, and return to the same perches with mechanical precision. Other insects come and go, unaware of the calculations unfolding around them. Occasionally, another absence appears where something was flying a moment before. The jet fighter passes through again, ancient and unchanged, enforcing rules written long before humans watched the sky and dreamed of flight. From the air, the seagrass meadows look almost unreal. Pale turquoise water spreads across shallow coastal shelves, stitched with darker green patches where grass grows thick and uninterrupted. Tides slide in and out, barely disturbing the surface, and sunlight penetrates all the way to the seabed, illuminating a world that feels suspended between land and open ocean. These meadows are not dramatic. There are no crashing waves, no jagged reefs, no obvious danger. And yet this is one of the most contested feeding grounds on Earth, a place where life persists under constant threat. From below, something large enters the frame. It does not rush in. It does not announce itself. A broad grey shape glides forward with patient momentum, its body barely flexing as it moves. The dugong looks less like a swimmer and more like a drifting object, a living blimp shaped by water rather than air. Its skin is thick and scarred, its back rounded, its flippers tucked close to the body. The face, when it comes into view, is unsettlingly familiar. Eyes set forward, lips heavy and expressive, the whole arrangement carrying an echo of something human. This resemblance, distorted through murky water and half-seen silhouettes, is what once seeded myths of mermaids among exhausted sailors. But there is nothing mystical here. This is a grazer, a specialist, an animal built to do one thing exceptionally well: eat seagrass, slowly and relentlessly, in a place full of teeth. The dugong's life revolves entirely around seagrass. Unlike most marine mammals, it does not supplement its diet with fish or invertebrates. It does not chase or hunt. It feeds on the underwater equivalent of pasture, cropping vast areas of vegetation with a precision that shapes the ecosystem itself. The secret lies in its mouth. The upper lip is thick, muscular, and deeply flexible, capable of curling inward like a prehensile nozzle. As the dugong lowers its head to the seabed, this lip grips the grass at the base, ripping whole plants from the sediment and drawing them into the mouth. Sand and debris are expelled, nutrient-rich shoots are swallowed. What remains behind are long feeding trails, furrows carved into the seabed that can persist for years, visible records of repeated visits to the same productive patches. These trails are not random. Dugongs show strong site fidelity, returning to familiar feeding grounds across seasons and even generations. Mothers teach calves the locations of reliable meadows, guiding them along established routes through shallow water. Over time, these repeated grazing paths influence the structure of the seagrass community, encouraging regrowth and preventing any single species from dominating. In this way, the dugong is not just a consumer, but a landscape engineer, maintaining meadow health through continuous, low-intensity disturbance. Remove the dugongs, and the grass changes, sometimes becoming overgrown and less resilient, sometimes collapsing entirely under stress. Everything about the dugong's physiology supports this slow, deliberate lifestyle. Beneath the skin lies a thick layer of blubber, providing insulation in cooler waters and acting as an energy reserve during periods when food becomes scarce. This fat is not armor. It does not protect against bites. Its purpose is metabolic stability. Dugongs burn energy slowly. Their resting heart rate is low, their movements economical. They are built for endurance, not speed. Breathing reflects this philosophy. A dugong surfaces gently, nostrils breaking the water for a brief controlled inhalation before sinking back down. There is no explosive exhale like that of dolphins or whales. The exchange is quiet, efficient. Oxygen is absorbed, carbon dioxide released, and the body returns to its underwater work. During longer dives, the dugong's heart rate slows further. Blood flow prioritized to vital organs while peripheral circulation decreases. Muscles tolerate low oxygen levels without panic. The animal does not fight its own physiology. It eases into stillness. This calm extends to social behavior. Dugongs are not solitary, but they are not tightly social either. They form loose associations, mothers with calves, small groups feeding in proximity, individuals crossing paths repeatedly over time. Communication is subtle, soft chirps, squeaks and trills that carry through water without drawing attention. These calls help maintain contact between mothers and young, coordinate movement, and signal distress without broadcasting presence to predators. The soundscape of a dugong meadow is subdued, a low-volume conversation in a dangerous neighborhood. That danger is constant. Tiger sharks patrol these same shallow waters, their striped bodies moving effortlessly through the murk. For them, a dugong is a high-value target, large, fatty, slow. Scars on dugong bodies tell the story of encounters survived. Crescent-shaped bite marks where sharks tested and failed, ripping flesh, but not finding a killing angle. Some individuals carry multiple such scars, evidence of repeated close calls over decades of life. So why stay? Why would a giant herbivore choose shark-infested coastal waters over the apparent safety of land? The answer lies in trade-offs that only make sense when viewed through evolutionary time. On land, an animal of this size would need speed, awareness, and defensive structures to survive predators. In the water, the dugong can exploit three advantages: depth, turbidity, and hearing. Shallow coastal zones are often cloudy, filled with suspended sediment that limits visibility. Sharks hunt effectively, but not perfectly, under these conditions. Dugongs compensate for poor eyesight with acute hearing, detecting changes in water movement and low-frequency sounds that signal approaching threats. When danger is sensed early enough, they reposition, moving closer to shore into even shallower water where large sharks are less maneuverable. Speed is not the dugong's defense. Caution is. It feeds with its head down, but surfaces frequently enough to remain oriented. It avoids open water when possible. It chooses meadows close to sandbanks, mangroves, or reef structures that complicate predator approaches. These decisions, repeated over a lifetime that can exceed 70 years, add up to survival. Most dugongs are not killed by sharks. They are killed by boats. Modern threats have reshaped the risk landscape in ways evolution did not anticipate. Dugongs evolved alongside predators that approached horizontally from water. Propellers and hulls arrive from above, silent and fast. Shallow feeding grounds intersect with shipping lanes, recreational boating routes, and coastal development. Collisions cause blunt trauma, deep lacerations, and internal injuries. Unlike shark attacks, which are often survived, boat strikes are frequently fatal. Add habitat loss from dredging, pollution, and climate-driven seagrass die-offs, and the dugong's carefully balanced niche becomes precarious. Yet the animal persists, precisely because its strategy is so narrow and consistent. Dugongs do not migrate across oceans. They shift locally, tracking seagrass growth in response to storms, floods, and seasonal changes. When cyclones tear up meadows, dugongs move on, sometimes traveling hundreds of kilometers along the coast to find new feeding grounds. When grass recovers, they return. Their memory of place is long, their attachment to productive areas profound. This persistence feeds back into the mythology surrounding them. A slow-moving, human-faced mammal surfacing rhythmically in shallow water invites projection. Early sailors, malnourished and isolated, saw what their brains were primed to see. But the reality is less romantic and more impressive. The dugong is not a half-human fantasy. It is a fully committed marine herbivore that made an irreversible choice millions of years ago and refined every system around that choice. It breaks rules that seem obvious. Large herbivores, by human logic, belong on land where plants are abundant and predators visible. Marine environments are for fast swimmers and armored giants. The dugong ignores that division. It chose a slow, plant-based life in water full of hunters and survived by becoming uninteresting, predictable, and calm. It does not provoke. It does not flee in panic. It simply exists, breathing in slow motion, shaping the seafloor with every mouthful. In doing so, it occupies a role no other animal fully replaces. Without dugongs, seagrass meadows lose a primary grazer that maintains balance. Fish communities shift, carbon storage changes, coastal ecosystems destabilize. The animal that looks passive and vulnerable is, in fact, a keystone. As the dugong finishes feeding, it lifts from the seabed, sand cascading from its lips. It turns with unhurried grace and glides away along a familiar route, following a trail carved by years of repetition. Above, sunlight ripples across the surface. Somewhere beyond the haze, a shark passes through the same space, missing the grazer by meters. The meadow settles back into stillness. This is not a creature that wins by force. It wins by choosing a niche that others ignore, by moving slowly in a fast world, and by trusting that consistency over time can be as powerful as any weapon. The rock looks dead. Sun-blasted sandstone rises in broken slabs, fractured by heat and age, its surface scoured smooth by wind that has been moving across this desert for millions of years. There is no shade worth naming, no vegetation tall enough to matter, no movement that catches the eye. The air shimmers, heat presses down like weight. In places like this, survival favors things that are small, fast, or hidden so deeply they may as well not exist. Then the rock opens. From a narrow crevice slides a head that does not belong in a land of minimalism. It is long and angular, eyes alert, jaw heavy with muscle. A forked tongue flicks out, sampling the air, retracts, flicks again, precise, rhythmic, deliberate. The body follows, unfolding from stone like machinery powering up. Muscular shoulders clear the gap, then a thick torso, then a tail so long and heavy it seems to arrive as a separate animal. The perentie has emerged, Australia's largest monitor lizard, and the illusion of emptiness evaporates instantly. This desert was never empty. It was occupied by something that knows how to disappear until it chooses not to. The perentie is a contradiction in flesh. In an environment where efficiency usually means shrinking, reducing mass, reducing water loss, reducing energy demands, this animal went in the opposite direction. Adult perentes can exceed 2.5 meters from snout to tail, with a build that suggests neither fragility nor compromise. Limbs are thick and powerful, claws curved and blunt enough to tear into soil, termite mounds, or carrion hide. The tail is a muscular whip, laterally compressed and capable of delivering bone-bruising strikes. Scales overlap in tight patterns, bead-like and tough, forming a hide that resists abrasion from rock and thorn alike. This is not a reptile that slips through cracks to avoid conflict. It is one that dominates space simply by occupying it. Yet size alone does not explain how the perentie survives here. The desert is unforgiving to excess. Every kilogram of body mass demands energy, water, and heat management. The perentie answers those demands with a physiology tuned for extremes. Like all reptiles, it is ectothermic, but that label hides complexity. The perentie does not passively accept ambient temperature. It actively manages it, basking early to raise body temperature rapidly, then retreating to shade, crevices, or burrows to prevent overheating. Its daily movements trace thermal gradients across the landscape, exploiting microclimates that smaller animals cannot access because they cool too quickly or overheat too fast. Size, in this case, becomes thermal inertia, an advantage that stabilizes internal conditions across brutal temperature swings. The head tilts. The tongue flicks again, faster now, each motion delivering chemical information to the Jacobson's organ in the roof of the mouth. This is not smell in the mammalian sense. It is spatial chemistry. Each fork of the tongue samples a slightly different part of the air, allowing the perentie to determine direction as well as presence. Scent trails become three-dimensional maps, layered over time. A carcass killed days ago, a burrow used at dawn, another monitor that passed hours earlier, all leave signatures that the perentie reads as effortlessly as text. This sensory system turns the desert into a database. The perentie does not wander blindly in search of food. It moves with intent, following invisible lines of information that link resources across kilometers of terrain. Carrion is detected long before it is visible. Nesting sites are located by the faint chemical residue of eggs and mammals. Other predators are tracked not to avoid them, but to exploit them. A perentie arriving at a kill site late is not necessarily disadvantaged. Its size and confidence allow it to displace smaller carnivores, stealing meals with little more than posture and presence. That confidence is backed by behavior that borders on unsettling intelligence. Perenties are not simple ambush predators. They investigate, they test, they learn. When raiding burrows, they do not dig blindly. They probe entrances, widen openings strategically, and adjust approach based on resistance. In some cases, they will return to the same burrow system repeatedly, timing visits to coincide with peak vulnerability of prey. This suggests not just instinct, but memory, an internal model of the landscape and its opportunities. Hunting is opportunistic and broad. Perenties consume insects, reptiles, birds, eggs, mammals, and carrion. They are equally comfortable pursuing live prey or dismantling what others leave behind. Their jaws are strong enough to crush bone, yet their feeding style remains measured rather than frenzied. Energy is conserved wherever possible. In a land where meals can be unpredictable, efficiency is survival. Occasionally, the perentie rises onto its hind legs, balancing its massive tail against the ground, body lifted upright. From this elevated position, it scans the horizon, eyes tracking movement far beyond the range of most reptiles. This posture is not common, but it is telling. It reflects an animal willing to break typical reptilian constraints when the situation demands it. The perentie does not behave like a simple ground-hugging lizard. It behaves like a surveillance platform, exploiting height, vision, and information in a landscape where knowing what is coming can matter more than reacting quickly. The question of venom complicates this picture further. For decades, monitor lizards were assumed to rely purely on mechanical damage and bacteria-laden bites to subdue prey. Modern research has revised that view. Perentes, like other large monitors, possess oral glands that produce compounds capable of lowering blood pressure and interfering with clotting. The venom is not potent in the dramatic sense. There is no rapid paralysis or instant death, but it does not need to be. Combined with deep, tearing bites and a mouthful of bacteria adapted to breaking down flesh, the result is a wound that keeps getting worse. Bleeding persists. Infection sets in. Prey, weakened by shock, blood loss, or sepsis, becomes easier to track and finish. This strategy aligns perfectly with the perentie's sensory strengths. A bitten animal that escapes is not lost. Its trail becomes stronger, not weaker, marked by blood and stress chemicals that light up the desert like a signal flare. The perentie does not need to outrun prey. It needs to outlast it. In this sense, the perentie's bite is less a killing blow and more a system hack, introducing cascading failures that unfold over time. Humans encountering perentes often underestimate this combination of hardware and behavior. The lizard may appear sluggish at rest, sunning itself like a statue, but when provoked it moves with startling speed. Defensive displays include hissing, gaping, and tail lashing, powerful enough to deter dogs and injure careless observers. Bites are rare but serious, not because of venom alone, but because of the layered damage they inflict. This is not a creature evolved to interact with humans, but it is one that commands respect when boundaries are crossed. Ecologically, the perentie occupies a role that few others can fill. As a top reptilian predator and dominant scavenger, it bridges gaps between trophic levels. It limits populations of smaller reptiles and mammals, cleans up carrion that might otherwise spread disease, and competes directly with introduced predators like foxes and feral cats. In some areas, its presence suppresses invasive species simply by making the landscape more dangerous for them. This effect is subtle but profound. Where perentes thrive, ecological relationships shift. So why does this animal shouldn't exist? Because deserts, by textbook logic, punish size. They reward creatures that minimize water loss, reduce caloric needs, and avoid exposure. The perentie ignores that advice. It invests in muscle, armor, brain power, and reach. It becomes a giant in a land of scarcity and survives by integrating every system, senses, behavior, physiology, into a coherent whole. This coherence is what makes the perentie feel almost artificial, like a cyberpunk dragon dropped into the outback. The sensory hardware reads chemical data like code. The body is overbuilt, modular, redundant. The behavior shows flexibility and learning. Nothing is wasted, yet nothing is minimized beyond necessity. It is an apex design that does not rely on any single trick, but on the integration of many. As the sun climbs higher, the perentie moves again, retreating toward shadow as rock surfaces grow too hot to touch. It slips back into the crevice it emerged from, body vanishing segment by segment until only the tail remains, then nothing at all. The desert returns to stillness, heat humming across stone. To the untrained eye, the land looks empty once more, but the system is still running. Somewhere beneath the rock, the perentie waits, tongue flicking in darkness, reading the desert's data stream, perfectly adapted to a place that should have rejected it and didn't.